Introduction. Low voltage, high current open bus bars are supported on insulators and carry current without a dedicated enclosure. They find application both outdoors and indoors and in AC and DC systems. High current open bus bars can be broadly classified into two major categories based on the electrical system. High current DC bus bars. High current AC bus bars. High current DC bus bars. Low voltage high current DC bus bars are installed in metal extraction plants such as aluminium, magnesium, sodium, potassium, calcium, lithium, and refining plants among many others. The magnitude of the current can be as high as 600 kA DC. The voltage at the rectifier terminal can be as high as 1650 volts DC. As an example, open bus bars connections are explained, in brief. In the aluminium extraction plant where the conductor material is aluminium, and base metal refining process, where the conductor material is copper. High current AC bus bars. Low voltage high current AC bus bars are installed in electric arc furnaces, EAF, and electric induction furnaces, EIF. Some of the very recent developments have DC voltage applied to the electric arc furnace electrodes. Open bus bars supported on medium voltage insulators had been used as connections between generator and generator transformer in power plants in early to middle of last century, before the development of isolated phase bus. This application is beyond the scope of the present discussion. Description. In the design of the high current bus bars, the following are the main criteria to be met. Limiting voltage drop. Limiting temperature rise of bus bars. Limiting losses in bus bars. Reducing stray magnetic fields. Ease of disconnection and shorting. Resistance to corrosive atmosphere. Temperature rise, losses, and voltage drop are all interrelated. While higher magnitudes of these parameters will result in a low capital cost and higher running cost, lower magnitudes will result in a high capital cost and lower running cost. The optimization parameters will depend upon the nature of the industry and the cost of energy. Over the years, the layout of open bus bars in most of the industries has been optimized and standardized for specific products. The emphasis, as always, is on low voltage drop, consequently low losses, and ease of connection and disconnection, necessitated by process operation and maintenance. Copper and aluminium have always been considered as the ideal conductors, and most industries have zeroed in on either one of the materials as a conductor. Resistance to corrosion in the operating atmosphere also dictates the choice of material. There is very little overlap in this selection. The extraction and refining industries are very capital intensive with proven process technologies, and any change from the existing practices is not readily entertained. Copper has always been used in the base metal electro-refining and electro-winning process and plants manufacturing chlorine derivatives. Aluminium has been the preferred metal in metal extraction plants. With the cost of energy ever creeping up, the efficiency of a plant is defined in terms of usage of kilowatt-hours per ton of metal produced. With aluminium having 60% of conductivity and 35% of the cost of copper by weight, industries are forced to rethink ways to save energy and capital cost. It is not uncommon to see high current DC connection having a combination of aluminium and copper bus bars in different sections of the plant. DC bus. Required power is tapped from the grid at the most optimum voltage and fed to a rectifier transformer. The low voltage winding is connected to a rectifier to obtain DC power at the desired voltage. A three-phase transformer with full wave rectification will deliver a rectified wave that has 6 peaks or pulses per cycle. A 6-phase transformer with full wave rectification will deliver a rectified wave that has 12 peaks or pulses per cycle. With phase shifting arrangement, it is possible to have a rectified wave having 24 pulses or 36 pulses per cycle. These pulses will be reflected as ripple contents or harmonics. It is obvious that with the increase in the number of pulses per cycle, the amplitude of the harmonics will come down and the rectified wave will resemble closer to a DC output. A 3-phase transformer with full wave rectification with 6-pulse rectifier will have a higher ripple content than a 6-phase transformer with full wave rectification with 12-pulse rectifier. The dominant harmonic for a 12-pulse rectifier is 11th and 13th harmonics. It can be theoretically established that the predominant harmonics will be twice the number of phases plus minus 1. 24 and 36 pulse rectifiers are also in use with associated phase shifting transformers in some plants. Diodes and thyristors have been used for rectification, and both these technologies compete in the market. Metal extraction plants for aluminium, magnesium, and many other metals have cells that require high DC current at low voltage. A single aluminium extraction plant may have several bays, also called pot lines, and each bay has several cells or pots. One such major plant has 11 pot lines and each line has 200 pots. The voltage across the cell is 4.5 volts and the current may vary from 200 kA to 600 kA. A higher DC voltage in a line reduces the capital cost, as it can accommodate more cells in series. The most energy-efficient electrical connection and physical layout would be to have 2 rows of cells, connected in series. The extreme ends of the connections are brought as close to each other as possible and connected to the output terminal of the rectifier. A typical cell dimension may be 12 meters, 40 feet, length by 3 meters, 10 feet, depth by 2.5 meters, 8 feet, height. Since the cells are connected in series, the current in all the cells will be the same. The voltage will, however, vary marginally, depending upon the charge parameters. Individual cells have a feedback system to maintain a constant voltage across the cell. This is beyond the scope of the discussion. It is necessary to keep the length of connections short and the number of joints least to reduce the voltage drop and associated loss of energy. It is necessary to have a facility for bypassing a cell when it is taken out for maintenance or rectification or replacement. This will ensure that the remaining cells are in operation while a bypass cell is being attended to. After the cell is made ready, the bypassing is removed and the cell is put back into operation. In the case of an aluminium extraction plant, carbon anode replacement is a part of the process as carbon is a consumable. Therefore, each cell has to be periodically bypassed and put back into operation after the anode replacement. The connections and disconnections are done using cranes and mechanical contraptions. The DC busbars in an aluminium extraction plant can be broadly classified as go and return conductor. It is a connection from the rectifier to the first cell and from the last cell back to the rectifier. Inter-cell conductor. It is a connection between the cathode of one cell to the anode of the next cell. To facilitate ease of disconnection, this section comprises a rigid bar welded to a laminated section with a rigid tab. Bolted joints need to be kept to a minimum. Shorting conductor. It is a rigid bar for bypassing a cell. For a pot line with a large number of cells in series, critical sections of the intercell and shorting cell connections can be manufactured at works and welded at the site. For sizing of the DC busbars, one need not consider the skin effect and proximity effect. Cell voltage for a particular metal is defined, and once the voltage drop between the two connecting ends is firmed up, the cross-section area of the conductor can be arrived at. Metal extraction plants are extremely power-intensive. Almost 1/3 of the cost of aluminium ingots can be attributed to the power consumption. With a pot line that is 1 kilometer long with 1,000 bolted joints, the efficiency, power loss, of the connection is of great importance. The voltage drop has to be limited to the extent practically feasible. The onward and return conductors are made of cast aluminium bars with a typical cross-section size of 200 mm, 8 inches, thickness by 600 mm, 24 inches, width. Such high DC currents are associated with a large unidirectional magnetic field. The magnetic field produced by DC will not induce eddy current or hysteresis losses in neighboring metallic objects. As stated elsewhere, the ripple contents in the DC, if significant, can be a cause of concern. Connections with copper. Here also the cells are connected in series and fed by a transformer-rectifier combination. The broad classification of the busbar systems in such plants comprise sub-assemblies as under: main busbars, inter and end cell busbars, shorting frames. Main busbars. Main busbars are routed as per the layout and mostly comprise factory-fabricated busbars bolted at the site. Inter and end cell busbars. Inter and end cell busbars are custom built for a project. They comprise a set of identical arrangement to keep a low inventory of busbars. Shorting frames in electrowinning plants have several copper laminates with spring-loaded contacts connected in parallel. AC bus. AC busbars form the connection to the terminals of the furnaces. The root length of busbars is small and in most cases the material is copper and the flexible connections are water-cooled cables. The busbars are exposed to some of the most hostile environments of temperature, dust, and chemically corrosive atmospheres. Electric arc furnace, EAF. In the electric arc furnace, an arc is struck between the electrode and the melt, and a constant current is maintained by a regulator. The power is drawn from the grid and fed to a furnace transformer. The output of the furnace transformer is fed to the 3 graphite electrodes, one for each of the R, Y and B phases. The graphite electrodes move vertically, up and down, to maintain a constant current through a feedback circuit. Graphite electrodes are connected by flexible, water-cooled copper conductors, to maintain the connection for the moving electrodes. A typical mid-sized furnace may have a transformer rated for 60 MVA with line current over 44 kA and a voltage varying between 400 volts to 900 volts. Currents of this magnitude can generate large electrodynamic forces between the cables. It can heat any metallic objects in the vicinity due to eddy currents losses and hysteresis losses. The contribution of heat generated by the furnace to the ambient is so high that induced losses have only a marginal contribution. The connection between the furnace transformer to the end of the cable is carried out by a rigid conductor. These are kept as short as possible. The flexible connection between the furnace terminals and the rigid conductor comprises several water-cooled, silicon-rubber insulated, braided copper conductors cables, connected in parallel. Electric induction furnace, EIF. In the electric induction furnace, the charge is subjected to heat generated by eddy currents and hysteresis losses. The furnace is used to melt ferrous and non-ferrous metals. Initially, the charge is heated and brought to the molten state, and subsequently, the induced currents mix and churn the melt to a uniform consistency. Eddy current losses are proportional to square of the maximum flex density multiplied by the square of the operating frequency. Hysteresis losses are proportional to the maximum flex density to the power 1.6 multiplied by the operating frequency. Non-ferrous material will be subjected only to eddy current losses, while the ferrous material will be subjected to eddy current and hysteresis losses. The frequency of inverter output varies between 50 cycles to 500 cycles depending upon the size of the furnace. The smaller furnaces have a higher frequency while the larger ones have a lower frequency. This is because the skin depth decreases with the increase in the frequency and reduces the churning capacity. Power is drawn from the grid and fed to a rectifier transformer. The DC voltage is fed to an inverter that has an output of high frequency. This power is fed to a coil that surrounds the charge. The charge is insulated from the power source. The copper coils are water-cooled. One of the largest induction furnaces has a rating of 65 tons with a power consumption of 42 megawatts. Water-cooled, silicon-rubber insulated, braided copper conductors cables, copper busbars and laminated copper flexibles are extensively used in these connections. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the Founder Director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.